Hi everyone, this is Stephen Downs once again with Ethics, Analytics, and the Duty of Care. And as you can see from the screen, today we're going to talk about explainable AI. This is part of Module 7, the decisions we make. Explainable AI is a difficult concept, and it's something that's come into vogue perhaps only over the last 5 years or so, although of course the concept of explanation has been around for decades, if not centuries. And it results from the fact that artificial intelligence and analytics applications can be, shall we say, opaque. So this has led bodies like the United Kingdom House of Lords to make declarations like, "We believe it is not acceptable to deploy any artificial intelligence system which could have a substantial impact on an individual's life unless it can generate a full and satisfactory explanation for the decisions it will take." So we can see here there's a clear link between the ethics of AI and the explainability of AI. For after all, how indeed will we evaluate the ethics of a particular decision that an AI made if we don't know why it made it? So that's good reason in itself to look deeper into this concept, and that's what we'll do in this video. Let's begin, though, by asking ourselves a more general question. What is an explanation? It's a concept really that, if it originates anywhere, originates in the philosophy of science. And we can go all the way back to people like David Hume, perhaps even to René Descartes, looking for theories of explanations of phenomena in the world. There are numerous ways of approaching it. I've got 4 here that can be drawn from the history of the philosophy of science. One is an explanation in terms of causality. What caused the accident at the corner? Now, that sounds like a simple sort of question, but we're going to find very quickly that causal explanations run into difficulties. Because there are different ways of looking at what a causal explanation is. I've indicated a few of these here. One is the distinction between internal causes and external causes. An internal cause is something internal to internal to the person or object in question. What caused the accident? We're looking at the driver for an internal cause. An external cause might be a condition like the sunlight shining through the windshield, the sleet or ice on the road, the bush obscuring the view, etc. A second aspect of causality is the concept of causal chains. And the reason for this is events happen in a sequence, and whatever we're trying to explain was only the latest in the sequence of events. So, there's a lot of TV shows that have a lot of fun with this idea. A person does something, and then something happens, and something else happens, something else happens, something else happens, and then something happens to the person originally that started the sequence of causes. Sometimes we can talk about the most recent part of that chain as the proximate cause, or the efficient cause. This is the thing that we say is the cause responsible for the event. But causality is a lot more complex, even than simple chains. There are complex causes where 2 things coming together create an event. And we can think of multiple simultaneous conditions that are necessary in order for an event to happen. It's like when the Space Shuttle Challenger exploded, right? You needed O-rings that were just wrong. You needed the temperature to be low. You needed a specific amount of stress on that particular part of the shuttle, and then it explodes. Even deeper, we look at the causes. Well, there were pressures to launch the shuttle early. There were decisions made that shortcutted the engineering and inspection process. A wide variety of things had to happen for that explosion to take place, and that's normal, not the exception. Finally, there's the concept of necessary and sufficient conditions, and a lot of people have trouble with this. I know that because I actually had to write a short article on it in order to correct people's confusion between the two. A necessary condition is a condition that must happen for something else to happen. For example, in order to graduate university, it is necessary to pay your tuition. However, just because something is a necessary condition does not mean that the effect will follow. Just because you pay your tuition doesn't mean you're going to graduate university. Other things have to happen as well. And we call these other things collectively the sufficient condition. If all of these happen together, that is sufficient for the event to happen. And what's interesting is there can be different sets of sufficient conditions leading to the same outcome. For example, one set of sufficient conditions is I pay my tuition, I study really hard, I pass my tests, and I graduate university. Another one is I pay my tuition, I cheat, I have someone take my exams for me, I graduate. Now, clearly one of them's unethical, but both of them are sufficient conditions to graduate. So, causal explanations right off the bat create issues. I could go on for the rest of the day about causal explanations, but maybe I won't. Another way of looking at explanations is as a product. As Bas van Fraassen explained in 1980 in his book, The Scientific Image, an explanation is an answer to a why question. Why did the accident take place? Why did I graduate? Why was my loan declined? Right? We're looking for an answer to that question. The thing is, he explained, the answer to why questions depend on a couple of things. First of all, they depend on presuppositions about causes and effects in the world. We're looking for some kind of story which will fit what we already understand about the world. Second thing is there's a set of alternatives where an explanation really is of the form, why this instead of that? Why are there roses in the garden instead of tulips? Why are there roses in the garden instead of nothing? Why are there roses in the garden instead of a pile of snow? You see, there can be different ranges of possibilities, and these ranges of possibilities determine what will count as an explanation. We can also think of explanation as a process. It's a type of reasoning called abduction. Now, you may have heard of deduction, where you infer from premises to a conclusion that necessarily follows. And you may have heard of induction, which is a type of reasoning where you have a bunch of events that happen, and then by induction or projection, you predict what the next event will be. Causality is arguably an inductive inference. Abduction is known as the inference to the best explanation. That's the phrase that Gilbert Harman gave it. But really the idea originates with Charles Sanders Peirce. The idea here is that if you see a phenomenon, you come up with a variety of different explanations as to why that phenomenon happened. And then you pick the best one. Well, what's the best one? Because presumably all of the explanations would work. Well, that's where it gets interesting. Best might be simplest. Best might be most believable. Best might be most convenient. Best might be the explanation that explains the most things. there are different choice criteria for picking the best explanation. It makes me think. I was just writing in my newsletter today about Larry Lawden, and the way Larry Lawden describes scientific progress is through the solution to problems. And that's really similar to the method of abduction being discussed here. And the idea here is what counts as progress in science is the ability to solve the next problem, whatever that is, however you solve it. And then the next problem, and then the next problem. And that's what progress is. And so what counts as rational or rationality on this model is whatever solves a problem. And so the inference to the best explanation is the explanation that most directly addresses the problem that you face. Finally, we can think of explanation in terms of justification. And very often this is what we really mean when we ask for an explanation, especially if we're asking a person for an explanation. Why did you pass through the red light? We're looking, an acceptable explanation might be that it was by accident or that the driver didn't notice. But really what we're looking for is some kind of reasoning like there were no other cars, I was in a hurry, somebody was dying, something like that. Something that can justify why this intentional action took place. So I think that that's going to be important later on as we look at how we try to understand what kind of decisions computers make, and in particular AIs and analytic systems make. So, why do we need this at all? Well, Hagres gives us a few examples of reasons, and we could argue that it all just comes down to human need. We just want to know. But what this really breaks down into is, a set of questions like the 5 here. Transparency. We need to be able to tell some kind of story in terms, in a format, and in a language that we can understand. Just to be able to replay it in our head. Or maybe we want to understand the underlying nature of the things that were involved in whatever happened. Typically, this is the causality picture, or it might appeal to a natural law or an essential trait. Joe stole the shirt because Joe just is a thief. I wouldn't think of that as a very good explanation, but it is the sort of thing that provides us with, an understanding of how the character of Joe would be what caused him to steal the shirt. Another one that comes up a lot is the question of bias, and the question here is, how can we ensure that the AI system isn't biased in some way? Certainly we've seen in all of the stuff that we've talked about so far in the course, there are many ways for an AI or analytic system to be biased. And really, it is argued, the only way we can be sure it isn't biased is if we're able to explain how it is that it came to the decision that it did. Similarly with fairness, we can only understand, it could be argued, how a system is fair if we understand how the decision was made. And finally, similarly, safety. How can we trust our system? How do we know that the AI won't go berserk and shoot us with a machine gun or whatever? Well, we could prevent it from having a machine gun in the first place. But failing that, we need to be confident in the reliability and the trustworthiness of our AI system, and arguably, we could only be confident if we know why it makes the decisions that it makes. When we started with artificial intelligence back in the days, the 60s, 70s, 80s, when AI was rule-based, and it was just a set of rules, and you'd have an environment, and you'd apply a rule to it and get a behavior out, then it was pretty simple to explain what was happening, because you just look and see what rule was triggered. Why did the heater start? Well, there was a rule that said if the temperature is less than 65, start the heater. This got a little bit trickier, okay, a lot trickier, once we got into expert systems and things like decision trees. And so now it's not a single rule that fires, it's a whole sequence of rules. But we can understand that, and then from the sequence of rules, we might be able to pick the rule that's the most salient or the most relevant to the current situation. It's a lot like picking out a single item from a causal chain. No problem. But then we got into neural nets, deep models, ensembles of different machine learning algorithms, and even into something which Google is here calling meta-learning, which basically is taking a whole bunch of these algorithms, pitting them against each other, eliminating 9, taking the 10th. Or I guess eliminating 8, taking the 9th. And so as machine learning has evolved, we've moved further and further away from explainability, further and further away from being able to, say, come up with a simple rule that we can point to, that we could say the AI followed this line of reasoning and that's why it did that. I talked earlier and several times through this course about how an analytics engine will take into account 60,000 factors, 60,000 variables. Of those, what is the one variable that constitutes a rule that allows us to explain the behavior? It's really hard to identify that variable to begin with, and secondly, to give it a name and to put it in a context that we could understand, and one that does not misrepresent what's actually happening in the AI engine. So then, what is explainability? Well, here's something from Gunning from a few years ago, not too long ago, trying to represent what explainable AI actually looks like. This is, I think it's an IBM presentation again. So, in the green boxes at the bottom there, we have different kinds of approaches to AI. So, the deep explanation will provide deep learning. The interpretable models will lead into things like Bayesian belief nets, etc. And then modal induction, like random forest or decision trees, are examples of the rule-based types of approach that we talked about earlier. Whatever they are, we have all of these different techniques that blend and mesh and get used together alone or in an ensemble. And what we're trying to do is pull from that something relatively simple and straightforward, like this table or this chart on the right-hand side, which gives us explainability. And so, it's just, from the red dot to the green dot, from the red dot to the green dot. That's what provides us our explainability. And it does so in terms of the nature and the accuracy of the prediction that it provides. That's the idea, right? The trick is going from these learning technologies to that explainable model. It's not obvious how to make that leap. The problem was intractable enough that the United States Defense Research Agency, DARPA, actually launched a project that they called Explainable AI, or XAI. And basically what it wanted to do is replace the learned function with a combination of explainable model and explanation interface, so that the person actually performing the task is able to understand why something happened or why something didn't happen, is able to know how to succeed or how to fail, and when to trust, and importantly, is able to figure out when the AI model erred in some way. And the argument is simply machine learning models are opaque, non-intuitive, and difficult to understand. A mechanism is needed to make that no longer the case. Okay, so we've sketched out the reasons for this and kind of what's involved. So how do we go about it? Well, what we want is, quote, a set of processes and methods that allows human users to comprehend and trust the results and outputs created by machine learning algorithms. Something that explains the model or describes the model that's being used. Remember, the model in an AI system, especially the neural nets that we've been talking about before, that's the set of all the connections between the individual entities, the actual connections that were formed and the weights of those connections as a result of the training. So, but I say that, I haven't really explained anything. What we need to do is explain why the model looks the way it does. And the big challenge is even in saying what the model looks like, because it's just a bunch of connections between thousands and thousands of neurons. The other thing it needs to describe is the expected impact. Is there a way of predicting what the model will do? If I had the model and I had some input, could I reliably predict what the outcome would be? Now, it's a little bit circular when you put it that way, because of course if I could predict what the outcome will be, I wouldn't need the model. But on the other hand, a big part of artificial intelligence, a big part of the motivation for AI is the idea that it's doing things and thinking like a human does, so that a human doesn't have to do it. And it can do what a human does many times faster, much more efficiently. So, it's artificial intelligence. So there should be a sense in which a human who approached the same thing would come to the same decision. Flag that. And then third, potential biases, right? That's kind of like being able to say, if it goes wrong, here's how it could go wrong. Here's my pre-trained model, here's my input. If there's a problem with it, here's how I would know that there's a problem with it. So the model, the impact, the biases. Three pretty essential conditions of explainable AI, and necessary conditions, we might say. So what's the process? Well, there's no single process to producing explainable AI, and it's going to be based on a variety of factors. But here's a process that I've pulled out of a document by IBM. It's fairly typical. We're looking at both the data and the model. We're looking at what the data is based on. Is it samples? Is it features? Where did it come from, etc., so that we have a handle on what the AI used in order to learn. Then the model. Are we looking at a local explanation based on something right here and now, samples, features, something like that? Or are we looking at a global explanation where we're able to talk about the model itself and not the specific prediction that the model has made? And there's two basic types of global explanations, a pre-hoc and a post-hoc explanation, and we'll talk about those. In a post-hoc system, what that's doing is producing an explanation for a specific decision, and ideally to make it reproducible on demand. Now, I've got a couple of examples here. something called LIME, Local Interoperable Model Agnostic Explanations, based on, quote, a class of potentially interpretable models such as linear models, decision trees, or rule lists. So those are AI models that are basically like those that we had at the beginning of the evolution of AI, where the AI itself is described as a set of rule-based processes. And then all we need to do is look at which rules were fired in the application of the AI. The other approach is black box explanations through transparent approximations. We'll come back and talk about this concept in a little bit, or this kind of approach in a little bit, where we're optimizing for two things, right? Fidelity to the original model, but also interpretability of the explanation. So really, I mean, we're approximating. We're not going to try to explain what every connection and every neuron in the model means, but we'll make an approximation of that. And I'll show in a little bit how we do that with something like fuzzy logic. The thing with post hoc systems is what's known as the fallacy of post hoc ergo propter hoc, which is Latin for after this, therefore because of this. It's pretty easy to come up with an explanation of something after the fact. And, you know, when we see the input, we see the model, we see the result, we can look at the model and say, well, yeah, I can sort of see how this part of the model might lead to that, or that part of the model might lead to that. So we're it's after the fact, and we can't necessarily say that simply because these things happened before and then this happened after, that these things were the cause of what happened. And so we're going to need something that actually allows us to predict what the outcome is going to be before it actually becomes the outcome. And that's how we get anti-hoc systems. And probably the most obvious of these is what's called a glass box approach, where when we build an AI, even a neural network, we're really able to say what every single one of the neurons in the neural network means. Now, we did an example of that in the video that began this module, where we had the number recognizer, and we had the input that came in of the diagram, and then the first layer were the edges, and then the second layer were the individual features, and then the final layer was putting the features together to produce the numbers. We have a similar sort of thing here, right, where we have primitives like lines that move in certain directions, and then subparts, which are combinations of these lines, and then object templates, which are even bigger combinations of the line, leading to exemplars that puts out our actual output that we've produced. So, glass box approach, we can see and understand everything that's happening. Problem is, that glass box approach becomes really difficult when the number of neurons enters the thousands, the tens of thousands, or even higher. Still, with anti-hoc methods, we still have various approaches that we can take. I really need to kill Microsoft Teams. There's this one person who keeps posting and posting and posting on Teams, and he won't stop. Okay, let me just, there we go. Quit. There, gone. Now my managers won't know that I'm working, but I'll live with that. Okay, so the Boolean classification rules via column generation is kind of a way of taking a really complex thing and pulling out of that some rules that we will say are going to be what I just stopped you. My goodness, I'm sure I quit. How can that continue to be? There just doesn't seem to be a way to stop Teams from sending me messages, even when I've quit Teams. It's very annoying. Okay. So I can't do anything about the little ding that's happening down there. All right. So a good example of this, and you've all seen this, is before a football game. And you have your analysts who give you, say, the 3 keys to victory. And here we have, and in honor of the Winnipeg Blue Bombers winning the Grey Cup last Sunday, we have one from the Blue Bombers. There's a thought. There, now there's no sound in my computer. I won't hear them, at least. So, continue protecting nickels in the pocket, right? So we can express that as a rule, something like, if the Blue Bombers protect nickels in the pocket, then that increases their chances of winning. And so they came up with 3 rules, 3 keys to victory. In this paper by Maliotov and Varshny, they did one for tennis. I don't like tennis, but I wanted to put it in here because it's a little bit more precise, right? So the predictive decision rule for Federer defeating Murray in the 2013 Australian Open was win more than 59% of 4-9 shot rallies, win more than 78% of points when serving at 30-30 or deuce, and serve less than 20% of serves into the body. Okay. But that always reminds me of the old joke, what's the key to victory in this hockey game? And the analyst comes along, well, Bob, you got to score more goals than the other team. Yeah, it's a little bit circular in that way. If you do the things that lead you to win, then you're going to win. So it's not ideal, but still, it's the sort of thing that people would accept as an explanation after the fact as to why Federer defeated Murray or why Winnipeg won the football game. Another approach can be characterized under the heading of contrastive explanations, and this actually opens up a whole range of possibilities, which I can't really go into, but basically what it does is considers why an event happened not in isolation, but instead of some other event. Now, this should remind you, and this is why I said it earlier, of an explanation as an answer to a why question. This is the mechanism that is used. So, for example, we have from Jacobi this example where we're trying to understand why it was decided to hire person X instead of person Y. Well, we could say that, person X was born, person X grew up, person X finished high school, all the sufficient conditions for being in a position to have been hired. But really, what we're after here is what was the significant difference between person X and person Y. Because they were both born. They both grew up. They both finished high school. They both have a relevant degree. But one of them had professional experience and the other one did not. So that becomes the contrastive selection. It's not that the one person had the degree. They both had the degree. It's that the one had the experience, the other one didn't. Now, again, this is going to depend a lot on the sort of difference that you think is important. Because it may also be true, for example, that person X was wearing a blue jacket and person Y was wearing a brown jacket. And we know, don't we, that people who wear brown jackets don't get hired into management. In fact, I had a director a number of years ago who fell out of favor with upper management. And in the months leading up to the time when he was let go, he expressed his protest by wearing brown jackets to meetings. I don't know if he even knew he was doing this consciously, but I could see it from the third-party perspective. He always wore the blue or gray jacket or the black jacket, and then he suddenly switched to brown, and then he was gone. I don't think he was let go because he wore brown jackets, but we wouldn't accept because somebody wore a blue jacket and not a brown jacket as a reason why they were hired. So what's the difference here? Well, this is an example of modal reasoning. Strictly speaking, it's a counterfactual because we have to consider the example of person Y and ask what would have allowed person Y to win the competition instead of person X, even if X won the competition, or what would not have been sufficient to make person X hired. So there's different analyses of this, but really it boils down to comparing what might be called possible worlds. And in possible world semantics, what you do is you imagine the closest possible world and then ask yourself what happened in that world. And the question now is, what defines the closest possible world? And I've mentioned this before, and the answer to that is salience. So in this case, what is salient is the professional experience and not the brown jacket. But you see what we've done here, right? We've presumed in our definition of salience what the actual explanation will be. So we've kind of begged the question, and that's probably the biggest weakness of the contrastive explanations method. As soon as you create these contrasting explanations, you're already putting in or embedding into your reasoning process something that will eventually count as your explanation. The way of knowing this is that in this case, I would not be able to rule out in any principled way the brown jacket explanation. All of this gets even more difficult when we're trying to interpret deep neural networks. Now remember from the discussion of models and interpretation before, to interpret something is to be able to provide in a broad sense, the semantics of a thing, or in a tighter sense, to be able to say what it means when we say two neurons are connected, or some neuron is turned on, or whatever. A way of doing that is to look at the data and then annotate it. So here we have some pictures here from a scanning electron microscope, and we can annotate those. We could say, like, there's a stocky thing here that's in a cross. There were some flowery things here. Here's the stocky thing again. Here's the flowery thing. Here's the stocky thing. Here's the flowery thing. Here's something weird. Here's the flowery thing, only small. And you see what I've done here, right? I've looked at those particular pictures, and then I've given them an interpretation. I've given them a description that we can latch onto and use to distinguish one from the other. And in fact, I could say, these are thick stalks, these are medium thick stalks, and these are sparse stalks, right? Big flower, medium-sized flowers, small flower. Still a weird thing. I don't know what that is. So now, if we just interpret the input layer, we've solved a big part of our problem with deep neural networks, right? Because now I've got a set of properties at the input layer that have labels, and I have an outcome at the output layer, which I can also give labels to, and then I could draw a set of rules. And if I drew them cleverly enough, then it wouldn't matter what's going on inside. I could have rules of thumb for what's actually happening in the neural net. But first of all, how do we justify that? And secondly, how do we kind of make that work? Well, that's where fuzzy logic comes in. The idea is to think of our layers in a neural network, our input layer, etc., in an approximate rather than a precise way. And that's what I did here, right? These are stocks. This is a flowery thing, right? So we're not using precise mathematical terms to describe these things. We're just being vague about it, or shall we say, fuzzy. Good example, and this is the way humans think, typically. A human, if you ask them, how should you drive when the road is bad? I say that because there's freezing rain going on right now, so it's a perfect example. They will say something like, if the distance to the car ahead is low, or even more accurately, if the car ahead is too close, and the road is slightly slippery, then slow down. Now, what does too close mean? Well, they say like 4 car lengths or whatever. But as Sheldon Cooper famously said, car length is not a proper measurement because cars can be variable lengths. But that doesn't bother us. We know what a car length is. If the road is slightly slippery, well, we're not going to do the coefficient of friction. It's either slippery or it's not. If you tap on the brake, you slide a little bit, that's slippery. I know, I've done that many times. Similarly, slow down. That doesn't mean reduce your speed 3.5 kilometers an hour. It means just let up a bit. So we can take precise numerical things and fuzzify them. And when we fuzzify them, instead of having to account for 60,000 input pixels, we really only need to account for maybe a few hundred possibilities. And that's the kind of thing that we can handle, right? The different ways of thinking of the distance, the different ways of thinking about the slipperiness of the road, the different ways of thinking of slow down. All of that adds up to a few hundred parameters. And these parameters are actually calculated differently for every driver. And that's fine. We expect that. A more experienced driver will think of slow as meaning something different from a less experienced driver. Or maybe the opposite. So that gives us a way of thinking about explainability in AI. How is that going to cash out in practice? Well, we've got basically a taxonomy of AI explainability that we can look at here. One-shot or interactive explanations. Come back to that. Are we looking at the data or the model, as we discussed earlier? Explanations of samples or distributions or features or vague, fuzzy descriptions. Explanations for individual samples or overall global behavior. Each of these specifies a different way that we're going to explain, and then the different ways that we're going to explain indicate the different kinds of systems we're going to use to actually produce the explanation. And these systems are separate explainability algorithms. And I'm not going to do the list of explainability algorithms. There is quite a list. But it's not going to advance our knowledge to go through that list. Suffice to say, answering these questions leads us to an algorithm selection process. So let's look at how this actually plays out. We've got an example from IBM here of explainability in practice. So what I'll do is bring this up on the screen. So here it is. And why don't I maximize so we get the best possible view? So let's suppose we're trying to explain the results of a loan application. So let's begin with the bank customer. All right. So we're going to pick someone. They were all denied. So pretty typical consumer experience. So let's pick Jason. So several features in Jason's application fall outside the acceptable range. So here's why he was denied. The value of consolidated risk markers is 65. The average age of account in months is 52, and it needs to be 68. The value of months since the most recent credit inquiry not within the last 7 days is 2, and it needs to be 3, which is kind of a weird criterion, but I guess they take that into account. And here are the relative weights of each of these 3 conditions. So the consolidated risk marker, whatever that means, right? But it'll be a list of indicators that they've just brought together. That's the most important factor. So you provide this to Jason. Jason says, yeah, okay. Jason will focus on the third one because people are irrational that way. But basically, what this is saying is you got to wait some time and maybe reduce your risk, and that'll get you the loan. All right. Good enough. So what about the loan officer? Now it's interesting in this example because here we have a case of Alice who was approved and Robert who was denied. And let's see what the loan officer is shown. Well, here are a whole bunch of parameters. Risk estimate, oldest trade open, average M in file, whatever that is, number of satisfactory trades, maximum delinquency ever, etc. So all of these are going to be factors, and they're being compared to other people who defaulted. Notice that they defaulted, and so you see, look at this. It's the same. You're seeing these places where it's exactly the same. But even up here, external risk estimate, they're kind of all in the same range. Here, he's similar to some of them. Here he's a little bit better than these others, but it doesn't seem to be a defining feature. So what we're getting here is a more detailed explanation for the loan officer, so that the loan officer has a more comprehensive explanation of why the AI recommended denying the loan, and then the loan officer will turn around to Jason, or Robert in this case, and say, sorry Robert, you're just too much of a risk, and Robert will go away unhappy. Meanwhile, we have the data scientist, and I love this because we've got directly interpretable models, or rules in linear terms learned from the FICO data set, whatever that is, and then some of these rules and the chart that's associated with the rule, etc. So this was actually the least reasonable of the bunch, but still, they're asking, what is the overall logic of the model in making decisions? The data scientist doesn't care about Jason or about Robert. The data scientist presumably cares about the operation of the model in general. So what we see here, therefore, are 3 different ways of presenting explanations that have very different characteristics to 3 different people. And I find that very interesting. So, what does that tell us? Well, I think we can draw some insights from the social sciences here. And there's a nice paper 3 years ago from Miller on exactly that. And I'm going to put it in the newsletter because it's definitely worth a read. And we want to think about, suppose the AI or the analytics engine was a person. Now, I know they're not. We all know they're not. But, we're people. We tend to anthropomorphize our computers, our systems anyways. So it's not going to be a big stretch for us to try to explain why the computer did something in the same sort of way we explain why a person did something. And even more to the point, we don't have access to the algorithm that's running the person. In fact, we're not even sure there is one. But probably is. But still, we don't have access to it. And even if we did, it's way too complicated for us to understand. So, I don't want to say, well, we make stuff up, because that's not really exactly the case. But we do come up with, and in fact, we have come up with an entire language for precisely this purpose. So, how do we explain behaviors? Well, for example, we might explain them in terms of intentions and intentionality. What we think they plan to do and how we think they think of things in the world, what objects they think there are, etc. What their person perception is, right? Which could be thought of in this case of how we see them as a person, what they are as a person by comparison to what I am as a person. So, I have certain intentions. I have a certain way of seeing the world. I think there are chairs. I think there are tables. I think there is a coffee cup. And I'm thirsty, so I form the intention to drink from it. I have drunk from it. Now I'm choking on it. Right? That kind of language is called folk psychology. And statements about beliefs, desires, hopes, fears, knowledge, all of these cognitive phenomena are the mechanisms or the tools that we use in order to explain someone's behavior. So, why did John rob the store? Because he believed he would get away with it and he needed the money. Perfectly satisfactory explanation. Zero reference to an algorithm or causes or any of the, it's if you really press it, we really haven't learned anything, right? Because we ask, well, why did he believe he would get away with it? Well, and we regress a bit further into these cognitive terms, and then we regress further, and we regress further, and we never do get to the level of neurons and algorithms, etc., because, well, first of all, we can't. We have to take what Dennett would call an intentional stance. We just, it's not really reducible, but we can just assume we're talking about the neurons and all of that stuff when we're talking about the beliefs and the desires, but we can fuzzify the connection between them, and that's fine. People do that all the time. And this actually goes back to Hume's point about causation, which I think is very relevant for this discussion. And Hume says, what is it for us to say that something is a cause and something is an effect? Well, it's a habitual association that we draw between the two. When we perceive them together long enough over time, they form a natural attachment in our mind, such that when we see the one, we come to expect the other to take place. That's a paraphrase, not a direct quote, but it's pretty close paraphrase. And our statements about beliefs, desires, etc. are the same sort of thing. We're probably not referring to anything actually real out there in the world. Just as there are not, for Hume, actual causes out of these mysterious forces, so also there are not really these actual beliefs or actual desires. They're interpretations that we create as he says, useful fictions. And you might think, how can you use a fiction for an explanation? And my answer is, well, why not? Does it solve the problem? Are we able to make progress with it? So, when we really want to get down to thinking about how to build AI systems, then we can't use beliefs, desires, etc. That doesn't work. But if we're trying to explain their behavior, then perhaps that language is perfectly acceptable. Let's suppose that it is. Then, now we look at the social sciences, which does work at that level of explanation for the most part, and look at the sorts of things that we accept as explanations in that language. Well, that would include things like norms and morals. For example, why didn't John rob the store? Well, he knew it would be wrong. Why did Fred wear the blue shirt? Because he had to wear something. I'm playing around with your alternative expectations there, right? Collective intelligence, and again, whole thing that could be made on collective intelligence. But if you're asking why did inflation rise? Well, people thought that there was a scarcity of things, so they were willing to pay more. That's an example of collective intelligence, right? We're actually giving masses of things like society attributes like beliefs and desires. The market wants to see lower unemployment this week. You hear that kind of language in the news all the time. We could use what's referred to as Mally's models to actually describe this. There's really, you could describe, you could approach Mally's models by thinking, first of all, of two ways that we talk about our expectations and how we describe them. First of all, what we actually think that is going to happen. We'll call that the informational approach. And then how that looks to other people. We'll call that the perceptual approach. We'll leave the perceptual approach to the side for now because it's not going to be relevant to the current discussion. But then when we look at the informational approach, we're looking at four major conditions: information requirements, information access, pragmatic goals, and functional capabilities. And so you can create these explanations of behaviors in terms of these four parameters. If these four parameters map to what we observe in the AI and the analytics, then that may provide us with a perfectly acceptable sort of explanation. Now, all of this is hypothetical. This whole field is just a few years old. But it seems, especially in a field like education, where we're kind of working that way all the time anyways, it feels like this sort of approach might serve as the best kind of approach. It would allow us to use the same kind of language and tools that we use to describe students and why they passed and fail, to describe AI systems and analytics engines and why they succeed or don't succeed. So what are the factors in these different types of explanation, and how can they go wrong? Well, here's a list, again from the Miller article. Things like, we take into account things like abnormality, temporality, controllability, intent, social norms, facts, foils or alternatives, responsibility, Coherence, simplicity, and generality, that helps us pick between alternative explanations, and even things like truth and probability. How plausible is the explanation that we've provided? But the danger in this kind of approach is the same danger that exists in AI generally, not surprisingly. Our folk psychological explanatory apparatus, that's a mouthful, might be biased. And here we have from Thagard and Kunda a simple example of somebody being pushed, right? So you look at somebody being pushed, how are you going to interpret that? How are you going to describe that to the police later on? Well, it turns out if the person that you see is black and if the person you see is white, you will actually draw a different interpretation and explain the action differently. The black person's push will be interpreted as aggressive. The white person's push will be negatively associated with the idea of it being aggressive. And so the black person's aggressive push might be thought of as a violent push, whereas the white person's push might be thought of as a jovial shove. Same physical action, two very different explanations as to what happened. And so the same thing that can happen in our explanations of AI can happen in AI itself. Or I should say that the other way around. The same thing that happens in AI can happen in our explanations of AI. So Miller, quoting Hilton, talking about conversational processes and causal explanations, comes up with the idea of explanation as conversation. And I found that intriguing. So there are basically two stages to this approach. First of all, a diagnosis of causality, in which the explainer determines why an event or an action happened. And it might refer back to some of the mechanisms that we've talked about already, right? Which means it might also still be flawed. But then there's the actual stage of providing the explanation. Now here, it's depicted as resolving a puzzle in the explainee or the listener's mind about why the event happened by closing a gap in his or her knowledge. So the presumption here with this particular account is that the explanation is accurate, and the way you resolve the need on the part of the person to have an explanation is that you provide the explanation, then you fill in the details around the explanation until the person is satisfied. Of course, in that conversational process, we could expect the pushback to win. In other words, we provide the explanation, but the person hearing the explanation in the course of the conversation is able to raise doubt as to the suitability or the satisfactoriness, if that's a word, of the explanation. And so you have to start over again, and maybe start the whole inferential process again. And that's a perfectly acceptable result. But what's really key about this is that there's no simple set of criteria, no simple rule, no simple mechanism that tells us how to explain and then how to present the explanation of a decision by analytics or AI. And that's really important. That makes it very clear that explanations are the sorts of things that happen rather less by rule and rather more on a case-by-case basis. And why should we have expected any other result? This is what we've been seeing pretty much consistently through this course. about how all of these systems work and how we approach ethical issues in general. So why would we expect explainability to be, some sort of magic pill which solves a problem, that gives us a simple process, would just provide an explanation and everything will be great, we don't need to worry about the fuzziness anymore? It's not how it works. And this really becomes clear when we think about what would count as explanations for different people. We saw an example of that in the IBM example. If we think about the very different domains of discourse that happen among different players or different stakeholders in the AI and analytics environment, we can see that what counts as an explanation is itself going to be very different. From the engineering perspective, we might be interested in control, performance, and discovering information. Somebody deploying an analytics engine will maybe need to explain its rationale or characterize its strengths or weaknesses, and perhaps, promote human-machine cooperation. Meanwhile, somebody who's working at the governance level will be more interested in trust, protecting against bias, following regulations and policies, and enabling human agency. These, ironically enough, all came from a Brookings Institute paper. And if they're getting that right, that shows how significant these different domains of discourse are. They say in their paper, this is why explainability will not save AI. And I actually agree with that statement. Explainability won't save AI because explainability is the same thing as AI. And that's perhaps the irony. When you throw out explainability as a criterion for the ethics or non-ethics of AI, basically you've thrown out the bulk of how we interact with each other as people. You've thrown out far more than you've kept of value. It's the classic throwing out the baby with the bathwater. I'm sorry for using such an obvious cliche. But these are all tools and mechanisms that we use every day. And sure, they're vague, they're fuzzy, they're context dependent. You couldn't possibly put them down in a row. And there are no simple explanations of why people see, do, or say things. And yet we still muddle through. We still interact with other people. We're even able to have court cases and find people guilty of an offense based on intentions, expectations, views of the world, wants, beliefs, desires, etc. If it's good enough for a human, arguably this kind of approach is going to be good enough for an artificial intelligence. And it goes back to what our expectations were at the beginning of all of this. Remember when we looked at the evolution of AI, we started with simple rules and then got into something more and more complex. Our understanding of how computers work hasn't evolved along with the computers. We're still in the simple rules stage, or must be declared in a functional program kind of stage of understanding of computers. But they are now far more complex than that, not as complex as people, obviously, but no longer resembling the simple rule-following engines that were created in the 1950s and the 1960s. We still use rules, just like we still use causality, just like we still use terminology like beliefs and desires and fears and hopes. And we don't worry about whether these things are precise. The terminology we use to tell us when to slow down or when our behavior was unacceptable or how to succeed at a baseball game are going to be fuzzy and general and probably not actual concrete representations of the situation, indeed if they are representations at all. And that's fine. And I think that over time, as we work with artificial intelligence and analytic systems, and as we become more used to how they operate and more comfortable with how they operate, our demand for precise explanations of why they did something every time will decrease. And, we don't demand an explanation of why the car goes 100 kilometers an hour. We don't demand an explanation of why our modem, well, I guess modems don't make sounds anymore, but when they did, we didn't ask for an explanation of it. I'm not asking for an explanation of why my computer screen has put up an image on the screen that I can see. And I think with artificial intelligence, our comfort levels will increase to the point where, we can come up with these explanations, and we will, and it'll be a fun exercise. But it will be about as important as identifying the 3 keys to the game for the Winnipeg Blue Bombers. That's it for explanation. This is the last really tough and technical section, I think, in the course. I'm going to wrap up Module 7 in the next video, and then we'll launch into Module 8, where I'm really going to try to begin tying together a lot of the different threads that we've unraveled through the first 7 modules of this course, and bring us to something like a satisfactory understanding of what we mean by ethics and analytics and the duty of care. I'm Stephen Downs. See you next time.